Hello students, welcome back. Previously, we went through the existence of GCD. Given pair of integers a and b, they exist a certain whole number d, in other words, non-negative integer d, such that it's a common divisor of a and b, in other words, d divides a and also d divides b. And finally, it can be written as a linear combination, ax plus by form, where x and y are integers. And that kind of number exists, the number with these three properties, green, blue, and red. Green, non-negative. Blue, common divisor. Red, linear combination. We prove that such a number exists. Now that existence is proved, we can go ahead with the properties. Before that, we could not really consider any kind of properties for something that may or may not exist. But now that we prove that it exists, we can consider the properties. Property number 1, d is greater than or equal to 0, and that comes directly from this, green. It's a whole number, so greater than or equal to 0. 0, 1, 2, 3, 4, and so on. Those are whole numbers, right? Second property, common divisor. D divides A and D divides B, and that's exactly the same as this blue property here. Property number 3. If there is another common divisor E, that is E divides A and E divides B, then E divides D. That makes D the greatest common divisor. As a matter of fact, we need this. If D is allowed to go negative, then this will give me something very negative, so it could be the smallest. But no, D is greater than or equal to 0, and E times something is D, and D has to be the greatest. And look at the color coding. This is clearly green, whole number. This is clearly blue. It's the same as this. But how about this red? Does it have something to do with this linear combination property here? The answer is yes, but it's not that obvious. Well, let's go ahead and prove it. Here we go. Green and blue are obvious. Let's go to red. If E divides A and E divides B, then we can prove that E divides ax plus by. If we prove that, then the conclusion follows because D is equal to ax plus by. You see? Ax plus by is equal to D. So yes, the conclusion follows. But the bold part, is this true? Well, we can prove it like this. E divides A, so E times some integer is A, so SE. E divides B, so E times some integer is B, say T times E. Then D, which is ax plus by, can be rewritten as, let's see, A is SE, so SEX, and B is TE, so TEY. Actually, it would have been better as TEY rather than ETY. Multiplication is commutative, so ETY is correct, but still, it looks better this way. B is TE, so TEY, so that's BY. And then E is common, so factor it out. What do you get? E times a certain integer is D. Consequently, E divides D. So, we proved the third property using this linear combination, and consequently, D is the greatest common divisor. Any common divisor divides D. And also, this proves the uniqueness of the greatest common divisor as well. Let's suppose there are two, D1 and D2. And D1 and D2 must satisfy all the properties here. And D1, let's apply the blue property. It's a common divisor, so you can replace D1 by E. And then D2, let's suppose it satisfies the red property. So D1 divides D2. And then we can do vice versa. Both D1 and D2 are GCDs with all these properties. So let's apply the blue property for D2. So D2 is a common divisor. In other words, yes. Replace E here. And then D1, let's apply the red property. So D2 divides D1. So D1 divides D2, and also D2 divides D1. And consequently, we can say D1 is equal to D2 because they are non-negative integers. Without that, we may end up with D1 is equal to negative of D2. But that's not going to happen because both are positive, both are non-negative. So the uniqueness follows. So what did we do? We proved the existence, which was really difficult. But once we have that, we can establish the properties: non-negative, common divisor, and the greatest common divisor. And also, we prove the uniqueness. So this unique number, D, is called the greatest common divisor. So something exists and that is unique. So we can define it. We define it as the greatest common divisor. Okay, we have a bit of time left, so let's go back to this proof here. And let's review the proofs a little bit because I left a couple of gaps there. It would have been a bit too difficult to fill up everything there and risk losing interest. So I left a couple of gaps there, and now's a good time to come back and pick those up. So a trivial case, we can define D as either this linear combination or that linear combination, yes. Either way, we have a whole number. So we have red and green, and we can manually prove the blue property as well. That's what we did. That was for trivial case for either A0 or B0 or both are zeros. Next, when A and B are both positive integers and we use induction on A plus B, and the base case is A plus B is equal to 2. When A and B are both equal to 1, in that case, we define D as this linear combination, and that's equal to 1, so it's a whole number. And that turns out to be 1. And 1 divides everything. So yes, we have the blue property as well. So that was a base case. Now, the inductive hypothesis, do you remember this? Assume A plus B is less than n, then the conclusion follows. And then under this assumption, let's prove for A plus B is equal to n, and we use this ingenious computation. A minus B plus B is less than n, so that we can use this. That's less than n, so we can use this, where A minus B replaces A in all these. Remember? That's red, that's green, blue, blue like that. Remember all those? And that's what we have here. Linear combination. And then that's a whole number. And D divides this. and D divides that, where A minus B replaces A. Please compare this and that. That's what we did. Are you totally comfortable with this? Because it is not 100% correct. There's a gap. Do you see the gap? There are two issues actually. Let's see, we are considering the case where A and B are positive integers, and based upon that we have this induction and A plus B. We have the base case, and that we are using the strong induction. So based upon this, these numbers A and B have to be positive integers. Here, B is positive, but how about A minus B? Is that positive? That's a problem. If yes, then we could use this inductive hypothesis and then get this conclusion. If no, then no in general. So we need some further work. And that was the gap. That's the gap I intentionally left out, because talking about all those minute detail will just lose interest and lose attention from everybody. So I didn't really do that at the time. But now I think it's a good time to talk about it. So when A minus B is greater than 0, that's fine. If not, we have a problem. Is there any way to handle it? Well, one way to handle it is to use this assumption without loss of generality. A is greater than or equal to B. Because one has to be either greater than or equal to the other, and everything is symmetric, so without loss of generality, let's assume A is greater. If B is greater than or equal to A, then let's just rename it. So A minus B is less than or equal to 0. We got up to here. Strictly less than 0, maybe not there yet, but less than or equal to 0, okay, we got up to here. If it is strictly greater than 0, fine, we can use the inductive hypothesis and we get this conclusion. We don't have to consider when this thing becomes negative, because we can rename A and B. Without loss of generality, we can assume this is greater than or equal to 0. That leaves the case when this thing becomes 0. In that case, I cannot use this inductive hypothesis. Instead, we can go back to step 1, which we proved already, and then use that to conclude the same, because we proved it already. So inductive hypothesis does not always guarantee this conclusion. This conclusion is always true, yes, but 99% of the time is coming from the inductive hypothesis, but the other 1% is coming from the trivial case through step 1. That's the gap I left last time, because it was a bit too minute. But now I think it's okay, so here we go. We covered everything now, so positive case is completely done. And as for the negative case and so on, yeah, detail is left to the students. So that really concludes the greatest common divisor: existence, properties, uniqueness, everything, including those minute gaps.